Mr. Causey here. I want to return to a result we proved in a previous video. When we multiply two complex numbers, the modulus is the product of the moduli of the two complex numbers, and the argument of the product of two complex numbers is the sum of the two arguments. Now, let's look at this a bit more closely. If we have two complex numbers, z1 is r1 cos theta 1 plus I sin theta 1, z2 is r2 cos theta 2 plus I sin theta 2, and we multiply these two complex numbers, modulus will become r1 r2, and an argument is theta 1 plus theta 2. Now that result can be extended in a natural way to cover n complex numbers. So let's get rid of that statement and let's extend the list to include n numbers. So there's the last one, Rn cos theta n plus I sin theta n, and let's multiply them all. Product of n of these complex numbers. Now the modulus will be the product of the moduli, and the argument will be the sum of the n arguments. An argument, not necessarily the principal value of the argument, might be out with that range. So there's the result, and that's a natural extension of the result we had. So let's change the two statements. There they are above. The modulus is the product of all these moduli, and the argument is the sum of all these arguments. It's a multiplicative property for the moduli, additive property for the arguments. So let's now attempt a question, and you can try this yourself if you stop the video, and then we'll tackle the solution to the problem. So let's take the sledgehammer approach and change each one of these complex numbers into its polar form. So Z1, let's look at the Argand diagram, 1 plus I. Let's locate it, and we'll draw a right angled triangle. You can see that root 2 and pi upon 4 are the modulus and argument. Now back to the diagram, 1 minus I, it's the mirror image in the x-axis of what we have for 1 plus I, so it'll have the same modulus of root 2, and its argument will be negative pi upon 4. So let's write that down. There's a polar form for Z2. So on to Z3, another diagram, and it's 1 plus root 3I. Make up a right angled triangle. The sides of 1 and root 3, so that would give us 2, and imagine it as half of an equilateral triangle, and the argument will be pi upon 3. So 2 and pi upon 3 for the modulus and the argument. And then finally 1 minus root 3I, and again that's the mirror image of the previous one in the real axis. So again it'll have a modulus of 2 and an argument of negative pi upon 3. So there's our final polar form, this one for Z4. So let's use the result that we multiply the moduli and we add the arguments. Pi upon 4 plus negative pi upon 4, it's just minus pi upon 4, and so on. So there we go. Root 2 times root 2 is 2, 2 times 2 times 2 is 8. And add up all these arguments and we get an argument of 0. And we know that cos 0 is 1 and sin 0 is 0. So that just gives us 8 for the final answer. Now that was, I suppose we could call it a sledgehammer approach. There's a more sophisticated approach which we're maybe going to have a look at now. So let's look at this alternative solution. Now you'll have noticed that Z2 is the conjugate of Z1. And what does that mean for arguments? It means that the argument of Z2 will be the negative argument of Z1. Likewise with pairs Z3 and Z4, Z4 is the conjugate of Z3, and therefore the argument of Z4 is the negative of the argument of Z3. You can see immediately when you add these four, you get 0. So the sum of the arguments is 0. And we haven't even had to work out what these arguments were. So now to find the product, remember we haven't found the moduli yet, and the modulus of a complex number and its conjugate are the same. And as before, there'll be root 2 and 2. So we multiply these four together with an argument of 0, and we get 8 as before. Now an interesting note that we can add to this is because conjugates are involved, let's look at a result that we proved in a previous video. That a complex number times its conjugate is equal to the modulus of that complex number squared. So Z1 times conjugate of Z1 will be the modulus of Z1 squared, and Z3 times the conjugate of Z3 will be the modulus of Z3 squared, and we know that's 2 times 4, which is 8 as before. Okay, let's go back now to the original result that we had, where we had a list of n potentially different complex numbers, Z1 up to Zn, and they had arguments of theta 1 up to theta n, the moduli R1 up to Rn. And remember, the result we were discussing was when you multiply all these, you multiply the moduli and add the arguments. So there's that result. Now let's consider they were all the same complex number. So Z1 to Zn now becomes Z, and they have moduli R and argument theta. And what happens then in this result? Well, we've got n z's multiplied together. That's written as z to the power n. We've got R multiplied by itself n times. And then, this is interesting, we've got n thetas added together. So that'll be n theta, just like 3 theta is theta plus theta plus theta, and so on. So the argument is n theta. So, in summary, if we raise a complex number to the power n, then its modulus gets raised to the power n, and its argument gets multiplied by n. So what I want to do now is to show you this in an interactive animated diagram so that we can just get a feel for the situation. So here's the diagram, back in the Argand diagram, and we have a complex number z. And remember, its modulus is represented by the length of this associated vector, and the argument, in this case positive, goes round from, well, there's the unit vector along the x-axis pointing to the number, real number 1. So we've got this complex number z, and let's have a look at z squared. Now let's think what's happening. Remember, we've just discovered that the modulus of z squared will be r squared, which is the modulus of z times itself. So really we're scaling this vector going out to z by a factor. In this case it's more than 1. There's the unit circle. So z has a modulus of more than 1, and when you multiply by a number that's greater than 1, then your associated vector will lengthen by that factor. And z cubed likewise will be even longer. Now, interesting now to note the angles, the arguments of these vectors. If we have an argument of theta for z, then z squared will be 2 theta, or theta plus theta. These angles, these two angles are equal. And for z cubed, the argument will be 3 theta. So theta plus theta plus theta. So we get the angles between each of these successive powers being equal, and all equal to the argument of z. So if I start moving z around, these angles are all still equal. If I move it out from the unit circle, you can see that scaling factor is now increasing. If we go inside the circle, then we've got a scaling factor that's less than 1, and therefore these associated vectors will be shrinking. The moduli will be shrinking by a factor of the modulus of z. That's r, which is less than 1 in this case. And interestingly, when we're on the unit circle, the modulus is 1, and when you keep multiplying by 1, it has no effect. So all of these associated vectors will be equal to the same length as that of z. So all these moduli are equal. Let's show a few more. There's z to the 4 and z to the 5. So let's move around again. Scaling factor means that as I go out from the unit circle, scaling factor is larger, and when I go in, the scaling factor is less than 1, and therefore the associated vectors will shrink in size. And on the unit circle, all the moduli are 1. Equal angles all the time between these. All these 4 angles or 5 angles, including this one, are all equal. So that maybe gives you a feel for this situation and what it means in the Argand diagram. So I'd like now to return to the original result that we got. And remember, in the demonstration we had complex numbers that lay on the unit circle. Now that would be those that have a modulus of 1. So let's suppose in this case we take the special case where the modulus is 1. And what happens to this result? Well, we've got z to the n equals 1 to the power n times cos n theta plus I sin n theta. Now remember, z in this case is just cos theta plus I sin theta. So we get the result that cos theta plus I sin theta raised to the power n is equal to cos n theta plus I sin n theta. And finally, we've reached de Moivre's theorem, or sometimes it's called de Moivre's formula. So cos theta plus I sin theta raised to the power n is the same as cos n theta plus I sin n theta, where you see the index of the power now becomes the factor in the argument, n times theta. So it's like the index moves down and becomes the part of the argument of that complex number. So that's Mr. Carsey signing out. Hope you enjoyed the video.